For inter-process communication problems, Dijkstra proposed a new variable type called semaphore together with two atomic operations down and up. The down operation on a semaphore checks to see if the value is greater than 0. If so, it decrements the value and just continues. If the value is 0, the process is blocked or put to sleep. The up operation on a semaphore increments the value of the semaphore addressed. If it becomes 1, the process wakes a sleeping process up and allows it to decrement semaphore. Checking the value, changing it, and possibly going to sleep are all done as a single indivisible action, hence are called as atomic actions. It is guaranteed that once the semaphore operation has started, no other process can access the semaphore until the operation has completed or is blocked. This is the code explaining what's going on in atomic operations of semaphores. Suppose that we have type definition integer semaphore. Semaphores are special kind of integer, and then there is a declaration of semaphore S set as 0. The down operation on semaphore S, while S is less than or equal to 0, do nothing. This is corresponding to blocking. Otherwise, S is decremented by 1. Up operation on semaphore S, incrementing the value of S by 1. Note that this is a blocking type and operations are atomic. If two processes try to execute ups or downs simultaneously, these operations will be executed sequentially in an arbitrary order. Here the code for use of semaphores for critical section problem is given. Mutex is defined as a semaphore. Initially it is set as 1. Mutex controls access to critical section. Any process I is such that it is executing in a while loop forever. It has the critical section and non-critical section as before. And just before entering the critical section, down operation is applied on mutex. So this is corresponding to critical section entry code. And after the critical section, there is up mutex, and this is corresponding to critical section exit code. And after that comes the non-critical section. Now let's consider the solution of the producer-consumer problem using semaphores. Define n as 100. This is number of slots in the buffer. Type definition integer semaphore. Semaphores are special kind of integer. Semaphore mutex is set as 1. Controls access to critical region. Semaphore empty set as n counts empty buffer slots. Semaphore full set as 0 counts full buffer slots. The code for the producer is as follows. Integer item, while true in the loop, item produce item, generate something to put in buffer, down empty, decrement empty count, down mutex, enter critical region, insert item, put new item in buffer, up mutex, leave critical region, up full, increment count of full slots. Just before the critical section, we have down and up operations on mutex, and also we are using other semaphores. Down empty is preventing the producer to insert a new item into the buffer if there is no more empty location. Here, up full operation is for waking up the consumer if consumer is sleeping. For the consumer part, again we have local variable item, while true, the infinity loop, down full, so it is checking if there is at least one item in the buffer, otherwise it will sleep here. Down mutex, this is for entry to the critical region. Item set as remove item, take item from buffer. Up mutex, this is the end of the critical region. And up empty, increment count of empty slots. So if producer is sleeping, this step wakes up the producer. Consume item, do something with the item. Be sure you understand that using TSL or exchange to prevent several CPUs from accessing the semaphore at the same time, producer or consumer busy waiting for the other to empty or fill the buffer are quite different. The semaphore operation will take only a few microseconds, whereas the producer or consumer might take arbitrarily long. Semaphores can also be used for process synchronization. For example, consider two concurrent processes, P1 and P2. Statement ST2 of P2 is required to be executed after statement ST1 of P1. In process P1, we have statement 1, and in process P2, we have statement 2. And we are requiring ST2 to be executed after ST1. Then use a semaphore sync, which is set to 0 initially. After statement 1, we have up sync, and before statement 2, we have down sync. If process P2 is faster and comes to S2 before ST1 statement of process 1, in that case, since the value of sync is 0, it will wait at this down operation until statement 1 here is executed and the value of sync is incremented by the up operation. After that point on, this process waiting in the down operation wakes up because the value of sync is 1, and then it decrements the value of sync and continues with the statement 2. Another synchronization example is given here. Consider two concurrent processes, P1 and P2. P1 and P2 are executing statement 1 and statement 2 respectively in an infinite loop. Statements ST1 and ST2 are required to be executed exactly as follows. Statement 1, statement 2, and then statement 1, statement 2 repeated forever. We have the code for process P1. It is executed in infinite loop. Here is the statement 1, and the process 2 has the same structure. At this line, it has statement 2. It is executed in a while loop forever. The solution is as follows. We have two semaphores, sync 1, 2, which is set as 0, and sync 2, 1, which is set as 1. In P1, we have down sync 2, 1, which is set to 1 initially, and then statement 1, and after that, up statement 1, 2. Here in process 2, we have down sync 1, 2, which is to be incremented here, and then statement 2, and up sync 2, 1. Initially sync 2, 1 is 1. If this one is faster, it will wait at this down statement because sync 1, 2 is 0. When process P1 comes here, it decrements the value of sync 2, 1 and executes statement 1. After that point, the value of sync 1, 2 is incremented by the up operation. And process 2 is then able to decrement the value of sycnhronization by the down operation and executes statement 2. If this is faster, if it has come to down statement, it should be waiting here until process 2 increments the value of synch21 by the up operation. So this is synchronizing for the execution statement 1 and statement 2 repetitively. A mutex is a shared variable that can be in one of two states, unlocked or locked. And it can be implemented in user space provided that a TSL or exchange instruction is available. The implementation of mutex lock and mutex unlock is given here. Mutex lock, TSL register mutex, copy mutex to register and set mutex to 1 by the test and set lock instruction. Compare register 0, check if mutex was 0, jump 0 equal to the point OK, OK is here. If it was 0, mutex was unlocked, so return. Here in the line labeled with OK, we have return. Return to caller, critical region entered. Call thread yield. Mutex is busy, schedule another thread. Jump mutex lock, jump to that point, try again the loop. For mutex unlock, move mutex 0, store a 0 in mutex, return to caller. Some of the Pthreads calls relating to mutexes. The name of the thread call is given here, and here is the description. Pthread mutex init, create a mutex. Pthread mutex destroy an existing mutex. Pthread mutex lock, acquire a lock or block. Pthread mutex try lock, acquire a lock or fail. Pthread mutex unlock, release a lock. In addition to mutexes, Pthreads offers a second synchronization mechanism, which are condition variables. Mutexes are good for allowing or blocking access to a critical region. Condition variables allow threads to block due to some condition not being met. Some of the Pthreads calls relating to condition variables are given here. The name of the thread calls are given in the first column and they are described in the second column. Pthread condition init, create a condition variable. Pthread condition destroy a condition variable. Pthread condition wait, block waiting for a signal. Pthread condition signal another thread and wake it up. Pthread condition broadcast, signal multiple threads and wake all of them. The pthread condition wait function blocks the calling thread on the condition variable cond and unlocks the associated mutex named mutex. The calling thread must have locked mutex before waiting on the condition variable. On return from the function, the mutex is again locked and owned by the calling thread. The calling thread is blocked until either another thread performs a signal or broadcast on the condition variable, a signal is delivered to the thread, or the thread is cancelled. Waiting on a condition variable is a cancellation point. In all cases, the thread reacquires the mutex before being unblocked. In this example, threads are used to solve the producer-consumer problem. The libraries standard input-output pthread are included. Maximum is defined as a large number. The mutex is defined as Pthread mutex T, and conc and conp are defined as Pthread conditional T. These are used for signaling, and also we have buffer, which is set as 0. Buffer is used between producer and consumer. In this example, instead of having a buffer of size n, we have a single item common between the producer and consumer. Only its value is updated as producer executes, and it is set to 0 when the consumer consumed it. In the producer thread, the parameter is ptr and it is void pointer type. And return value is again void pointer because this is a thread. Integer I is a local variable for the producer. There is a for loop here. The for loop is repeated max number of times. I is set to 1, while I is less than max. Each time I is incremented by 1. Pthread mutex lock is called on the mutex. So get exclusive access to buffer. This is locking the mutex. While buffer not equal to 0, that means that if the item is not consumed yet, pthread condition wait is called with parameters condition on producer conp defined here, and the related mutex is the mutex defined there. The mutex should be locked before as given here. If the condition is met, the mutex is locked and it continues. Otherwise, the process waits here until the condition is met. When it is able to continue, buffer is set as I, put item in buffer, and then pthread condition signal, condition C. So this is sending a signal to wake up consumer. Then we have pthread mutex unlock. The mutex is unlocked, so release access to buffer. After this is repeated maximum number of times, the pthread exit is called with parameter 0. The producer terminates. In the consumer part, again the parameter is void pointer ptr and return type is void pointer. We have local variable integer I. For I from 1 up to max, each time I is incremented. This is repeated maximum number of times. Pthread mutex lock is called on the mutex, get exclusive access to buffer. While buffer is 0, pthread condition wait, condition C, the mutex is called. Buffer is set to 0 if it is able to continue. Take item out of buffer. Pthread condition signal, condition P, backup producer, pthread mutex, unlock the mutex, release access to buffer. By considering this producer and consumer, producer is executed and then consumer one by one. In the main part, pthread, T-type, pro and con are defined. Then pthread mutex init is called with the parameter mutex and it is initialized to 0. Then pthread cont init is called, condition C is initialized to 0. Pthread cont init on condition P, which is initialized to 0 also. Here pthread create is called with parameters con given here with parameter 0 and consumer is to be executed when the thread is started, and this is the value of the argument. And then the thread producer is created in the same way. Pthread join pro 0, pthread join con 0 are called. Here there is a call to the pthread join. It waits until pro terminates, and another pthread join with parameter con. It waits until con terminates. Pthread condition destroy to destroy the conditional variable conc, and similarly destroy cont P, and Pthread mutex destroy to destroy the mutex variable, the mutex. There has been an assumption that multiple processes have access to at least some shared memory. If processes have disjoint address spaces, how can this be achieved? There are two answers. First, shared data structures, such as semaphores, can be stored in the kernel and accessed only by the means of system calls. Second, most operating systems, including Unix and Windows, offer a way for processes to share some portion of their address space with other processes. Other synchronization primitives are as follows. Futex, fast user space mutex. A futex is a feature of Linux that implements basic locking, much like a mutex, but avoids dropping into the kernel unless it really has to. Monitors is a higher level synchronization primitive. Remark: semaphores are level and monitors are not usable except in a few programming languages. And also both do not allow information exchange between machines. We have message passing primitives such as send destination and message, receive source and message. Also, barriers are other synchronization primitives. Use of a barrier is explained here. Suppose that we have several processes as A, B, C, D. They are approaching a barrier. Whichever arrives to the barrier before the others wait there. When the last process also arrives to the barrier, all of them are led through the barrier.